In this assignment, you will implement the Butterworth frequency filter to produce gradual transitions across the cutoff thresholds in the frequency domain. And by doing so, you avoid the ripple and ringing artifacts that we see with the ideal filters. The code is extremely similar to what you saw in lesson 7 for ideal filters, except that here we use the Butterworth transfer functions instead of the binary transfer function, and the formula for that is provided in these notebooks. As before, we have a project notebook and a solution notebook, and the links are provided in the description of this video. So let's click on the project notebook. So here's our function. Again, it takes an image, a lower cutoff frequency, an upper cutoff frequency, and also an order. The default is 2. As before, you need to cast the image to float32 data type. Then you take the forward Fourier transform using CV2's DFT function. Then you can use NumPy's shift function to shift it. Then you compute your frequency grid by using a mesh grid that creates the U and V, the horizontal and vertical frequency indices. And then you compute the radius as we showed in the previous lesson. And finally, you get to the main difference between this and the ideal filters. Here you implement your Butterworth low-pass and high-pass filters. The formula for the low-pass transfer function is this, and the high-pass transfer function is this over here. So that's quite simple. You just implement those. And then to create the Butterworth mask, we simply multiply the low pass and the high pass, and we cast it as a float32 type. Then you apply the mask as before to both the real and imaginary components of your Fourier transformed image. That creates your filtered Fourier transform. And then you have to take the inverse of that. So first you inverse shift or unshift the Fourier transform, and then you use CV2's inverse Fourier transform function to get your filtered image. And you have to remember to set the correct flags for the inverse Fourier transform in CV2. And also for the purpose of visualization, you will compute the magnitude spectrum. Again, you use CV2's magnitude function to and feed it the real and imaginary components of the Fourier transform. And then don't forget that you have to take the log of that in order to create a displayable magnitude spectrum. You return both of those. And then here we just apply your function to an image to see if you can create low pass, high pass, and band pass filters without creating ripple artifacts.